All right, we're going to talk about Ampere's law today. But before we do that, we have to talk about, we have to do a little bit of review for an electric field. That our first definition for electric field was K dq over r squared, r hat, where remember that there was, this is the force on some charged particle is given to us by the integral of r squared times the distribution of its charge in the r hat direction. Okay, and so if the charge is negative, then it's in the negative direction. If it's positive, it's in the positive direction. Doing the math on this, however, is a colossal pain in the rear and is beyond the scope of this class to do it over and over and over again. So instead of that, we came up with this. That the electric flux is defined as the integral of E dot dA, okay, becoming a much easier way of figuring this out, giving us our which equals our enclosed charge over epsilon naught. Okay, and the beauty of this is we don't use this unless we are picking a dA that is highly symmetrical, and so the math works out nice. So it's 4/3 pi r, 4/3 pi r cubed for a sphere, or it's it's 2 pi rh for the length of a wire, or something for a cylindrical Gaussian surface. That's why we use this, is to make this math a lot easier. And when we get this, we have this location of positive charges, and we'd have a sphere around it. And as long as we chose a surface that is symmetrical around our charge, then we're good with the math here. Magnetic fields are different, though. Okay, magnetic fields, we have something similar. Okay, we have B equal to mu naught I over 4 pi integral of ds times r hat over r squared. Now, I hope you guys remembered yesterday I asked you guys to look for a similarity between this and our electric field, right? Mm-hmm. Well, here's a constant. There's a constant. dq. Okay, and this time it's ds. But isn't ds really the incremental difference in the current as we move along? Right? Because if we have this I in there, okay, it's really an incremental difference in the current. So it's sort of related to the charge over r squared cross r hat. Okay, where this is a dot in here. No, there's no dot. It's just times. It redirects it in the r hat direction. Okay, but we've taken this to give us a new version of that, which is, well, we'll get to that in our next lecture. It's integral of b dot ds is equal to mu naught I enclosed. Okay, so this is meaning that our ds, that this path that we're examining our field in, is closed. Okay, we start where we begin. Okay, and we don't want to do the math for this either. We do this so that we can choose our ds to be a closed loop, which is called an Amperian loop. Okay, just as we picked this to be a Gaussian surface, we picked this to be an Amperian loop. Now, why just a loop? Is it possible to surround a current with the surface area? You can't really get to the end of the current, right? Okay, you can't enclose the current in something, but you can draw the loop around it. Okay, and so that's the purpose of this being an Amperian loop. All right, so let's look at this for a second. So we're going to draw a plane here. All right, and we have a current. Going through our plane. Our current is in the I direction. Or that is our current, it's not in the I direction. And then we're going to draw our field lines around this. So where's that going to be? We take our thumb, right? We point in the direction of our current, and our field is going to loop around and I'm not okay. These are supposed to be equally spaced. Okay, I didn't do that so well, but they are supposed to be equally spaced, so that it's this counterclockwise rotation around the eye, as we have it drawn here. Okay, you guys are cool with that with the right hand rule, yeah? All right. Well, we can take any portion of this and call it ds. Okay, so that's our ds, and from here we have our r. Okay, our distance from the wire out to our spot. Well, if we do this, if we have a loop, then what's ds? What is how far are we traveling as we go around? It's 2 pi r, right? The length of s is the total length of s is 2 pi times whatever this radius is. Okay, so that's why we can do this. In fact, it's almost always going to be 2 pi r. Okay, because you're drawing a loop, right? And most loops are generally circles. Okay, so we get to draw. We get to take this 2 pi, and our integral of BDS okay, well, the field's going to be constant, so we're going to take this out. And the integral of ds, well, that's just, okay, well, we're going to take our magnetic field, which is going to be, well, we learned this from Biot-Savart law, right? What our magnetic field is around this line? Okay, at any particular point, okay, do we want to go back to that? And where we figured that, where are we? Where did I find you? Where are you? Yes. Oh, right. It was in there. Okay, that if our wire, remember this, that if our wire, here's our situation, we did this for a wire, and then we extended our wire forever. We got this cosine theta 1 minus cosine theta 2. But if theta 1 and theta 2, if the wire goes on forever, theta 1 and theta 2 approach 0 and 180. Okay, which creates this for an infinite wire. And I wanted you guys to memorize this, yeah? That the magnetic field close to an infinite wire is given to us as mu dot I over 2 pi. Well, in this case, it's going to be r, because that's the distance from the wire. Just ringing a bell? All right. So that's just b, though. Here's the beautiful thing. This is what's so awesome about it. That's just b times the integral of ds, which is 2 pi r. Well, son of a gun. Okay, where am I? I am here. Okay, which gives us, those guys cancel, And so the integral of B dot ds is equal to mu naught times the current enclosed. Well, doesn't that look familiar? Okay. Look at our Gauss's law. Right? They're almost exactly the same. Uh-huh. Except, well, right, but it has this enclosed value. The value that's giving us the field, okay, is the enclosed. It's the amount that our surface, or the amount that our loop encloses, is here. But mu naught is really just the magnetic version of E naught, right? Of epsilon naught. Okay. So, okay, and when we do this, we always want. Now, I could have done this. Let's come back to this picture. I could very easily have done this with I could very easily have chosen a loop. Okay, raise your hand if you want to integrate this. Okay, right, nobody does except for Shun. Shun does. Okay, Shun is a masochist. And Omar's back there showing solidarity with Shun, so I appreciate that. Right on, power. Okay, I didn't say that. Okay, magnetic power, or yeah. Okay. So that wasn't. No, I'm. Race has absolutely nothing to do with your magnetism. All right, so we're gonna do an example here. Oh yeah. Okay. Given. We are given this. We are given a wire. In this wire, we have a uniform current. Okay, or a current density, shall we say, that the current per cross area, okay, is the amount of current going through this cross area is uniform. You follow me there? That there are no fluctuations in the current density as we go through this wire. Okay, in fact, we had this variable before. It's called J. Okay, it just means that it's evenly distributed throughout the wire. Okay, I want you to find. Oh, I'm sorry. This is of radius r. Sorry, capital R. All right, and we're going to find this. Find B in the situation where, okay, R is less than capital R. I'm sorry, no, greater than. We're going to start with greater than, and then we're going to do less than. All right, so the radius at which we're studying the magnetic field is either completely outside the wire or it is inside the wire. All right. So for A, we have integral of B dot ds equals mu naught I enclosed. Okay, but we're taking a loop, right? We're going to look at the magnetic field that is, current is going this way, so it's going to go, we're going to go in that direction, okay, for our magnetic field. Okay, and this distance r, okay, is greater than that r. So our field okay, but how much is enclosed? This loop encloses how much of the current? So b times 2 pi r, because that's the result of the integral, okay, is going to equal mu naught times all of the current. Okay, so that brings us back to b equals mu naught I over 2 pi r. Well, duh, because we've already figured this out in a previous problem, just in a different way, right? We found what is the magnetic field at this point for an infinitely long wire. Right, we found that. That was we came out with this value is the magnetic field. Okay. B is a little different. Okay, we still have the same thing, except this time the I enclosed, the current enclosed, is actually inside our radius. So here's our little r. So how much do we actually have inside of that?
Density.
Uh-huh. Right, well, this becomes b times 2 pi r equals mu naught I enclosed. But the I enclosed is going to equal to the current
Wait, that's dry ice, right? Is it gonna explode? Oh! Oh no!
Okay. Okay, that our I enclosed, okay, is going to equal the ratio of those, because it's going to be equal the ratio of the areas. Is going to be the total area, total current enclosed. Yeah? All right, so this becomes mu naught I r squared over r squared, and one of those r's goes away there. Okay, and we are left with our magnetic field equaling mu naught I over 2 pi r squared, which is the whole thing, times r. And so it is proportional to how far you are outside, how far you are in the wire.
Wait, is it ours?
Okay, so we're going to graph this.
Is it r squared in the bottom, or is it just r?
This is r squared on the bottom. Oh, I'm sorry, I didn't cross it. I didn't bring it over from here. So, if our I'm sorry, we're going to graph magnetic field versus radius in this situation. Because it varies as varies with r as long as we're inside the conductor. Okay, it's going to be linear out to the point where this is mu naught I over 2 pi r. Okay, then it trails off as 1 over r as we move away. Okay, and this is, it asymptotes at 0. Okay, and it maximizes at mu naught I over 2 pi r. Okay, piecewise function.
Piecewise.
Piecewise. See, piece. Okay.
Should put Z.
And that is it for Ampere's law.